scientists detected alarming activity on the San Andreas Fault that could trigger a major earthquake. Ever wondered what keeps geologists and seismologists up at night? What if I told you that beneath California's picturesque landscapes, a seismic time bomb is ticking louder than it has in centuries? The San Andreas Fault is no stranger to devastating earthquakes, but what makes the current situation particularly alarming is the presence of multiple overdue segments along this infamous fracture in Earth's crust. When we say a fault segment is overdue, we're referring to sections that have accumulated stress for longer than their typical recurrence interval, essentially zones where pressure has been building up without the release of a significant earthquake. Take the southern segment of the San Andreas Fault, which runs from the Salton Sea through San Bernardino and into the San Gabriel Mountains. Historical records and paleoseismic data reveal this segment ruptures approximately every 150 to 200 years on average. The last major rupture? Around 1726, nearly 300 years ago. That's a century beyond what we'd expect based on historical patterns, making this segment especially concerning to seismologists. This isn't just about exceeding arbitrary timelines, though. Modern geodetic measurements using GPS stations across California show accelerating strain accumulation rates in key segments of the fault system. These instruments measure how much ground on either side of the fault is moving relative to each other. In a healthy fault that regularly releases stress, we'd see periodic spikes followed by drops in accumulation. Instead, what we're observing is a steady ramping up of strain energy, like a rubber band being stretched further and further without snapping back. Recent data reveals strain accumulation in the southern San Andreas segment has increased by approximately 20 to 25% over average rates in the past decade. This acceleration doesn't guarantee an imminent earthquake, but it dramatically increases the probability. Every year of additional strain accumulation compounds the issue, with some models suggesting the fault is now capable of producing a magnitude 7.8 or larger earthquake, an event that would release energy equivalent to roughly 500 Hiroshima-sized atomic bombs. When specialists analyze the current stress distribution map of the San Andreas system, several danger zones emerge. Using sophisticated computer modeling based on GPS data, fault geometry, and historical earthquake records, scientists have identified what they call stress shadows and stress concentrations. Stress shadows are areas where previous earthquakes have temporarily relieved pressure, while stress concentrations are zones where pressure is abnormally high. The junction where the San Andreas meets the Garlock Fault represents one such stress concentration point. This intersection, located near the town of Gorman, shows disturbing signs of pressure buildup. Another hotspot lies in the Mojave segment between Palmdale and San Bernardino, where modeling indicates stress levels may have reached 90% of what the rock can withstand before rupturing. When rocks are subjected to stress approaching their breaking point, even small additional forces can trigger failure, like the proverbial straw that breaks the camel's back. How do scientists know all this? The monitoring technology deployed along the San Andreas system today is leagues beyond what was available even a decade ago. A network of over 250 continuous GPS stations measures ground movement with millimeter precision. Interferometric synthetic aperture radar, or INSAR, satellites detect even slight deformations in the Earth's surface. Meanwhile, deep borehole strain meters and tilt meters record incredibly subtle changes in rock strain and ground tilt that might precede major events. These modern instruments have revealed concerning patterns that were invisible to previous generations of scientists. For example, we now know that silent slip events, slow movements along fault planes that don't generate noticeable earthquakes, have been occurring more frequently in the Coachella Valley section. These silent slip events can redistribute stress in dangerous ways, potentially loading adjacent locked segments beyond their breaking point. Perhaps most worrying is what satellite data tells us about the 300-year dormant southern segment. Using space-based synthetic aperture radar, scientists have mapped the interseismic deformation field, essentially a visualization of where strain is accumulating versus where it's being released through minor movements. The southern segment shows almost no minor stress release, behaving like a completely locked door with pressure building on both sides. Historical analysis suggests this segment has produced earthquakes ranging from magnitude 7.5 to 8.2 in the past, forces powerful enough to permanently reshape landscapes. What makes this particular dormant period so concerning to experts? It's not just its duration, but how it compares to patterns before previous major earthquakes in the region. Paleoseismic studies, where geologists dig trenches across fault lines to find evidence of ancient earthquakes, reveal that unusually long quiet periods have preceded some of the largest earthquakes in the fault's history. The current 300-year gap exceeds any dormant period we found evidence for in at least the past 1,500 years of the southern segment's history. The concept of seismic gaps further amplifies these concerns. Seismic gaps are sections of active faults that haven't ruptured recently, while adjacent segments have. They represent potential energy reservoirs where stress continues to accumulate. The southern San Andreas hosts what seismologists consider the most dangerous seismic gap in North America. If this gap were to rupture along its entire length, models predict a rupture that could propagate over 200 miles, affecting everything from the Mexican border through Los Angeles County. How would such a rupture scenario play out? Unlike the popular conception of earthquakes as brief events, a complete rupture of the southern San Andreas would unfold like a zipper being undone, with the rupture front traveling at roughly 2 miles per second. Communities would experience violent shaking not just for seconds but potentially minutes as the rupture propagates. The unprecedented length of this dormant period suggests the eventual rupture could affect a larger area than typically expected. When we examine historical records of similarly overdue fault segments worldwide, the pattern becomes even more concerning. In nearly every documented case, from the 2004 Sumatra earthquake to the 2011 Tohoku event in Japan, unusually long dormant periods preceded earthquakes that exceeded the expected magnitude range. These examples suggest that longer waiting periods don't mean the fault has somehow settled down. Quite the opposite. They indicate that when release finally comes, it may be more violent than the historical average would predict. While the long-term pressure buildup is certainly concerning, it's the recent unusual activities detected along the San Andreas Fault that have truly set alarm bells ringing in the scientific community. These aren't just subtle changes that require specialized knowledge to understand. They represent significant departures from baseline behavior that suggests something fundamental may be changing within this complex fault system. The Parkfield segment of the San Andreas has long been nicknamed the earthquake capital of the world due to its remarkably consistent behavior. Located roughly halfway between San Francisco and Los Angeles, this segment has produced magnitude 6 earthquakes approximately every 22 years since records began, in 1857, 1881, 1901, 1922, 1934, 1966, and most recently in 2004. This clockwork-like regularity made Parkfield the perfect natural laboratory for earthquake studies. Scientists packed the area with monitoring equipment, hoping to capture the next predictable quake in unprecedented detail. What they're seeing now is deeply troubling. The seismic pattern signature in Parkfield over the past 24 months bears striking similarities to what was observed in the 2 years preceding the 2004 earthquake, but with crucial differences that suggest even greater energy potential. Specifically, the pattern of foreshocks, smaller earthquakes that sometimes precede larger ones, shows an acceleration curve that's approximately 40% steeper than what preceded the 2004 event. When scientists overlay these patterns on a time series graph, the current trajectory suggests we're witnessing the same sequence, but with significantly more energy involved. Even more concerning is the unprecedented clustering of microseismicity in historically quiet areas. Microseismicity refers to very small earthquakes, typically below magnitude 2.0, that aren't felt by humans but are readily detected by sensitive instruments. Under normal conditions, these tiny quakes occur randomly across the fault system. However, since late 2023, scientists have documented unusual clustering patterns, groups of micro-earthquakes occurring in tight spatial and temporal clusters in segments that historically show very little activity. One such cluster has formed near the junction of the San Andreas and San Jacinto faults near San Bernardino. This area experienced over 1,200 micro-earthquakes in an 8-month period, compared to the historical average of fewer than 200 per year. More tellingly, these clusters show a pattern seismologists call migration. They're slowly moving northward along the fault at a rate of approximately 2 to 3 kilometers per year. Similar migration patterns were documented before the 2019 Ridge Crest earthquake sequence and the devastating 1992 Landers earthquake. Satellite data has revealed equally alarming ground deformation patterns that weren't possible to detect before the era of advanced space-based radar. The European Space Agency's Sentinel-1 satellites, which can measure ground movement with millimeter precision, have detected what scientists call anomalous uplift and subsidence patterns, essentially areas where the ground is bulging upward or sinking downward in ways that differ from historical norms. A particularly concerning deformation signal emerged in early 2024 near the Cajon Pass, a critical juncture where the San Andreas Fault makes a dramatic bend. Here, INSAR data shows an uplift rate nearly triple the historical average, suggesting fluid migration or deep pressure changes along the fault zone. Similar bulging patterns were observed before several major earthquakes globally, including prior to the 2009 L'Aquila earthquake in Italy that killed over 300 people. Deep beneath the surface, another troubling sign has emerged: an increase in non-volcanic tremors. Unlike regular earthquakes, these tremors are slow, low-frequency seismic events that typically occur much deeper in the crust, often 15 to 30 kilometers down. They're believed to represent slow slip along the deeper portions of fault zones where temperature and pressure conditions create a transitional behavior between brittle fracture and plastic flow. Have you ever wondered what it would feel like to detect these early warning signs of a major earthquake if you were living along the San Andreas Fault? What would you do differently today if you knew a magnitude 8 earthquake was truly imminent? Would you prepare more extensively, relocate temporarily, or continue life as normal? Share your thoughts in the comments below. The frequency of these deep tremors along the central section of the San Andreas has increased by approximately 230% since 2021. More worrying still is their spatial progression. They appear to be migrating towards sections of the fault that are fully locked and accumulating strain. In earthquake physics, this is akin to watching pressure build against a dam that's showing signs of weakening at its base. Equally troubling are the unusual attenuation parameters recently measured across the fault system. Attenuation refers to how seismic waves lose energy as they travel through rock. By analyzing how waves from small earthquakes decay as they move through the fault zone, scientists can infer properties of the subsurface environment. Recent measurements show decreased attenuation in several key segments, meaning seismic waves are maintaining their energy over longer distances than expected. This change indicates that the fault zone rocks are becoming more homogeneous and less fractured, essentially healing and locking up. When fault zones become more uniformly locked, they tend to rupture more completely and violently when they finally fail. These attenuation changes are particularly pronounced in the Carrizo Plain segment, which last ruptured in the massive Fort Tejon earthquake of 1857. Slow slip events, episodes where faults move too slowly to generate significant seismic waves, have also been accelerating beyond normal baseline measurements. These events typically release strain gradually without causing damaging earthquakes, acting as a kind of safety valve in the fault system. However, monitoring networks have detected a 70% decrease in slow slip movement along the southern San Andreas since 2020, suggesting this natural pressure relief mechanism may be failing. When scientists conduct comparative analyses with precursor patterns before major historical earthquakes, the similarities become even more unnerving. The current combination of signals, increased microseismicity in unusual locations, accelerating deep tremors, anomalous ground deformation, and reduced slow-slip events, bears a striking resemblance to the seismic landscape documented in the years preceding the devastating 2011 Tohoku earthquake in Japan. That event was preceded by similarly unusual patterns that in hindsight clearly indicated fundamental changes in the fault system. Unfortunately, their significance wasn't fully appreciated until after the magnitude 9.0 earthquake and the resulting tsunami claimed over 20,000 lives. The parallel patterns now observed along the San Andreas represent what one USGS scientist recently called the most concerning constellation of precursory signals I've seen in my 30-year career. To understand why these unusual fault activities are so concerning, we need to dive into the scientific mechanisms that actually trigger major earthquakes. When seismologists observe abnormal patterns, they're not simply pattern matching. They're recognizing specific physical processes that can culminate in catastrophic failure along a fault system. The most fundamental mechanism at work is stress transfer dynamics, how pressure builds and releases across interconnected fault networks. The San Andreas isn't a single clean fracture, but rather a complex system of primary and secondary faults that interact with each other. When one segment moves, even slightly, it redistributes stress to adjacent segments. This process follows principles similar to load-bearing structures in engineering. Remove one support beam and the load shifts to others. Recent seismic data reveals concerning stress transfer patterns throughout the San Andreas network. The 2019 ridge crest earthquakes, though not directly on the San Andreas, transferred significant stress to the Garlock Fault, which itself connects to the San Andreas system. Calculations show the ridge crest sequence added stress equivalent to about 3 to 5 years of normal tectonic loading onto certain San Andreas segments. This sudden stress addition, combined with the already accumulated strain from centuries of loading, pushes the system closer to failure. Critical threshold mechanics further explains why the current situation is precarious. Rocks under stress behave somewhat like materials in engineering stress tests. They can withstand increasing pressure up to a critical point, beyond which sudden catastrophic failure occurs. Laboratory experiments show that rocks approaching their breaking threshold display subtly different behaviors, including increased microcracking activity and changes in seismic wave velocities through the material. The patterns of microseismicity we're currently witnessing match these laboratory predictors of imminent failure. What makes this particularly concerning is that different segments of the fault may be approaching their respective thresholds simultaneously. Historically, major San Andreas ruptures have typically involved single segments failing in isolation. However, when multiple adjacent segments are highly stressed, there's potential for a multi-segment rupture, a much larger earthquake than what we've seen in California's recorded history. Fluid migration patterns represent another critical triggering mechanism currently at play. Water and other fluids deep in the crust can dramatically influence fault behavior by changing the effective stress on fault surfaces. When fluids infiltrate a fault zone, they reduce the friction that normally keeps fault surfaces locked together, essentially lubricating the fault. Recent monitoring using electromagnetic surveying techniques has detected unusual fluid concentration changes at depth along several San Andreas segments. The source of these fluids remains somewhat mysterious, but leading hypotheses include deeper mantle processes or climate-related changes in groundwater infiltration patterns. Whatever their origin, these fluid migrations appear to correlate with the changing patterns of microseismicity and tremor activity. The San Andreas segments showing the most pronounced fluid signature changes are the same ones exhibiting increased deep tremors, a correlation that has preceded major earthquakes in other fault systems globally. Perhaps the most concerning is the potential for a cascading failure model to unfold. In this scenario, a moderate earthquake in one segment triggers failure on adjacent segments in a domino effect, resulting in a much larger event than any individual segment could generate alone. The 2002 Denali earthquake in Alaska demonstrated this process dramatically. What began as a magnitude 6.7 event on the Sustina Glacier Fault triggered the main Denali Fault, eventually rupturing over 200 miles of faults in a complex sequence that resulted in a magnitude 7.9 earthquake. The current San Andreas configuration appears particularly vulnerable to such cascading scenarios. Models run on supercomputers at the Southern California Earthquake Center suggest that if a rupture begins on the southernmost portion of the fault, there's now a 35 to 40% chance it could continue northward through multiple segments, potentially creating a magnitude 8+ event affecting both Los Angeles and San Francisco metropolitan areas. This probability has increased from earlier estimates of 20 to 25%, reflecting the changing stress conditions throughout the system. So what does all this scientific evidence tell us? After examining the concerning strain accumulation patterns, the unusual seismic activity clusters, and the multiple triggering mechanisms at play, the message is clear. The San Andreas Fault system is showing multiple signs of entering a critical state that has historically preceded major earthquakes. While we can't predict exactly when the fault will rupture, the convergence of evidence suggests we're in a period of significantly elevated risk. The 300-year dormant period, combined with accelerating strain rates and unusual seismic patterns, creates what one seismologist called a perfect storm of risk factors. For Californians and those living along the fault, this isn't just academic science, it's a call to action. Emergency preparedness isn't just prudent, it's essential. From securing heavy furniture and maintaining emergency supplies to understanding evacuation routes and retrofitting vulnerable structures, the time for preparation is now, before the ground begins to shake. The San Andreas Fault will eventually release its accumulated energy. That's a geological certainty. Whether that happens tomorrow or decades from now, the scientific indicators suggest the clock is ticking faster than we previously thought. By understanding these warning signs and taking appropriate action, we can transform this scientific knowledge into something truly valuable: resilience in the face of one of nature's most powerful forces. If you found this information valuable, please take a moment to like this video and subscribe to our channel for more in-depth scientific explorations. Hit that notification bell to stay updated on our latest uploads, and let us know in the comments what earthquake-related topics you'd like us to cover next. As always, stay insanely curious.